So welcome back. This next one. Consider a parallel plate capacitor. So that tells me it's a uniform field that is used to create a uniform field. That's kind of nice. 9-volt battery is connected between the plates. The plates have a gap of 2 meters. Express the electric field in volts per meter or newtons per coulomb. So, okay. What we learned, if I think about my box, this was force and this was field, and this was delta U and this was delta V. And if I wanted to go from force to that, I multiplied by D, some kind of length. If I want to go from there, I'm going to multiply by some kind of length. Okay, so what that tells me is, oh, if I want to find my electric field, if I want to find my electric field, what I do is my E is equal to my delta V divided by some kind of length. Let's call it D. More commonly we'd call it, well, let's call it D is from there to there. Often it's called delta X. Yeah. So I say, oh, well, in that case, then my E is equal to, let's get these right, my delta V is equal to 9 volts, and my D is equal to 2 meters. So my E is going to be 9 over 2, which equals 4.5 volts per meter. And that is, can I justify, yeah, actually I can. If I want to go and change this electric field into a force, what would I do? I would divide, I would multiply by Q, yeah? And if I want to go from this change in potential, which is measured in volts, to a change in potential energy, which is measured in, oh, yeah, I'm not sure I can. That would be in joules, so that would be times, that would be times Q. So if I multiply, all right, I'm just going to cut because I'm losing my trend. But basically, volts per meter is the same as joules per coulomb. Okay, joules per coulomb equals 4.5 joules per coulomb. I can justify it. I can relatively easy by saying that volt per meter. Volt is a joule per coulomb meter, and this is a Newton meter per coulomb meter, and that is a Newton per coulomb. So volts per meter is dimensionally exactly the same as a Newton per coulomb. It's the same stuff. It's like the difference between impulse and change in momentum. The two different names, two different sets of letters, but they're the same thing. Yeah. So it's that same idea. Cool. So next, we do what the book is doing. It says, all right, we're going to use this same methodology, and we're going to look at a complicated situation. So here we are. Here's our parent charge on top of this mountain. And then we're going to take not another charge, but a point of interest, and go from somewhere on the side of the mountain. We're going to go around the mountain, and we're going to go away. Is that a question?
Yeah.
Yeah.
In the exercise before, so it was either A or B, but we would need the charge to know, right?
Let's have a look. No, it's 4.5 and 4.5. It's B, because that one's not right. These two are exactly the same thing. So if they have the same units, they've got the same value.
So the charge doesn't matter if it's the charge of whatever is in there, because we just said
we've not put a charge there. The charges are on here and the charges are on there, and they're not changing.
Okay.
So it's just like I kind of down here. I'm sorry, I kind of I thought I could show a clever way of showing it, and I got lost. That's the danger of kind of doing things live like that. So yeah, it's just remember that volts per meter is the same as newtons per coulomb, and the justification is dimensionally they are exactly the same. Cool. Now, in terms of what force would I have if I put a charge inside there, that's a different ball game. We can, then we're talking about another charge. So with this, the visualization is I'm on a volcano. I went to Mount Vesuvius, and I'm near the top, and I walk kind of like a spiral path down the side of the mountain. And what's my change in kinetic energy, change in potential energy per kilogram of me? What's the change in potential in doing this journey? And we know that change in potential is equal to minus the integral of E dot ds. And now this is where I need to have a good diagram, because my little ds is this little thing, because now they're not all just going to be the same, they're all going to be different. My little ds here is going to have a different angle to my field. It's going to have a different value of the field strength is going to be bigger. So E is going to be bigger, theta is going to be bigger. It's going to be a mess. I'm going to add all these guys up. There's a whole bunch of them. So we're going to take this generic case and do some stuff. So we say my change in potential is equal to minus E dot ds. Remember, for a point charge, the E is equal to Ke times Q over R squared times the unit vector R. We're dealing with a point charge, so we've got to include this. So E dot ds is equal to Ke times Q over R squared times the unit vector, and we're going to dot that with ds. So we can dot we just dot the vector bit. So we dot that unit vector with ds. Unit vectors have a magnitude of 1, so that unit vector has a magnitude of 1. So I can say its magnitude will be the magnitude of 1 times the magnitude of ds, that's how long this little line ds is, times the cosine of the angle between those two. And the cosine is going to change. That angle there is going to change for different steps in this journey. So that's not going to be a constant. So we're going to take the generic case, and here's the generic case. I'm going to draw it big. There's my ds. Here's my little change in my radius. And then we have that. And there's my theta. And what we say is that for that triangle, dr is going to be ds cosine theta, just by using trig. Yeah, that's a right angle. So dr equals ds cosine theta. So now if I look back at this thing, I get E dot ds, for this little guy, E dot ds is equal to Keq over R squared. That's not changed. But now I can put down, rather than R dot ds, or 1 times ds times the cosine of theta, I can say, I can say 1 times ds times the cosine of theta. That's just that. But I recognize, look, ds cosine theta equals dr. So we get Ke times Q over R squared dr. Can you see what I just did? I changed it so my integral has the variable in terms of what I want to integrate with respect to. And we've done that a whole bunch of times through this course. We keep finding that the variable is not the same as the thing we want to integrate with respect to, so we change the thing we want to integrate to. We find some relationship. We did the linear density when we did some Gauss's law stuff. It's the same same physics principles. The math is always the same, but it's the same physics principle. So then I say, well, okay, delta V is equal to minus the integral of E dot ds, which equals minus the integral of Keq over R squared dr. I know how to do that. It's going to be minus Keq minus 1 over R. And so for my two integral points, it's Keq 1 over Rb minus 1 over Ra. The final radius minus the initial radius. So this is important. Points to recognize. Your direction on the compass does not matter. All that matters is the change in, well, not the change, but the relative lengths, relative radial distances. The direction doesn't matter. So I can throw a whole bunch at you, giving you different directions in with precision. So you throw all that stuff away. All you want is your distance from the charge, your distance from the charge. And it's an inverse relationship. That's kind of interesting. Before, we had inverse square, and now we've got inverse. It only depends upon one charge because there's no other charge moving. I'm not talking about change in potential energy. I'm talking about change in potential. Okay? Which is like change in height. Okay. So we say, what is the potential difference between a point which is 3 meters to the north? So here I go, plus 2, 3 meters to the north, 1, 2, 3. So there's my P initial of a 2 column charge, and a second point that is 6 meters to the south. Oh my word! What do I? Is this positive and negative? What is this? I don't know. 1, 2, 3, 4, 5, 6. There's my P2. This is plus 3 meters. This is minus 6 meters, and I want to find my change in potential. Change in potential equals, what was it, minus KE Q over, times 1 over R final minus 1 over R initial. Agreed? So we get delta V equals minus KE. My Q was plus 2 times 1 over, this is 6, not minus 6, it's 6 away. It's a radial measurement. Doesn't matter about the sign. 1 over 6 minus 1 over 3. Delta V is equal to minus KE 2. 1 over 6 minus 2 over 6. Shame on me. I should have made it a different number so it doesn't come out as... When the answer equals one of the two original factors, it's confusing. Minus KE times 2 times 1 over 6. Minus 1 over 6, isn't it? Yeah. Minus 1 over 6. So delta V is equal to plus 2 over 6, which equals plus 1 over 3, which equals plus 0.33 volts. Okay? Oh, I forgot my KE. So, oh man, I was just about to say, don't forget your KE. KE. Okay? So I went from boom, boom. I went from there basically to there. Oh, rats. Bad Bonaquisti. So minus and minus make a plus. So I have no positive sign there. I remembered that guy and I forgot that guy. So it's positive. And why did I know to go back and check? Because I knew the answer was wrong. And why did I know the answer was wrong? Because I'm going downhill. So my potential must be negative. So that has to be negative. Because that was a positive, and that was a positive, and that was a positive. Duh. Okay. But you notice I check myself visually. I am a more visual thinker, but I check myself visually. So I catch mistakes. If you don't check yourself visually, you've got to have those equations and all the signs just cold. I just find it easier. I suppose the reason why I've never got them cold is because I can survive by just looking at my diagram and saying, oh, it should be a negative sign there. That's a mistake. No, it's there. False. In the test, you can leave, so let's write this out nicely. In the test, you can leave the KE. You can't leave pies, but you can leave the KE. Negative, yeah. I'm forgetting it, aren't I? That stubbornly is not going in my brain. Cool? Okay. 35 Coulomb positive charge is located at the origin. Oh, man. What is the change in potential energy that is experienced by a 2 Coulomb positive charge as it moves from a point that is located at 1, 2, 3, so we have plus 2 Coulomb, to a point which is 1, 2, 3, 4, 5, 6, 7. The path does not matter. All that matters is that where we start and where we end. What do I know? I know R final is equal to 7 meters. I know R initial is equal to 3 meters. I got that from there, didn't I? I know that little q is equal to plus 2 coulombs. I know that big Q is equal to plus 35 coulombs. I'm going to draw my whoosh, whoosh. I'm starting off close by and ending up there. I'm going downhill. This is my plus 35. Positive charges are like volcanoes. Negative charges are like sinkholes. So then I say, well, let's have a look. We learned that delta V is equal to KE Q. What do we have? 1 over R final minus 1 over R initial. Am I doing that right again? No, yes, I'm doing that right. So delta V is equal to KE. Now, which Q? Well, really, this is the parent charge. That's really big Q, which is that guy. I'm going to eventually, but I'm working out my change in potential at the minute. This is my change in potential, which is per unit charge. So it's the change in energy per unit charge. I'm going to multiply by 2 in the end. But at the moment I'm working in potential. And potential is all about the mother charge and not about the charge that's moving. There's no charge there's no need for a charge to be moving. In this example back here, there was no charge moving. It was just a point of interest. Okay? So I'm going to deal with voltage, then I'm going to put the charge in. The little charge in. Okay? So just bear with me and we'll get there. Okay? So delta V equals KE, and that Q is the plus 35. And this is 1 over the final, and the final we end up at is 7 minus 1 over 2. So delta V is equal to KE. Oh, 3. I'm glad you guys are here. That's all I can say. So that's going to be 3 over 21 minus 7 over 21. So this is delta V is equal to KE 35 times minus 4 over 21. And that would be volts per coulomb. That'd be volts, I'm sorry, which equals joules per coulomb. Okay? So delta U is equal to Q times delta V. So delta U, which is what I want what is the change in potential energy, not potential, but potential energy, is equal to plus 2 times KE times 35 times minus 4 over 21. So delta U is equal to, man, what's that going to be? 70 times 4 is 280. That's minus 280 over 21 KE. If I did that right, got my calculator with me. 280 divided by 21 equals, that's going to be 13.33. So minus 13.33. And what the unit's going to be? What the unit's going to be? What the unit's going to be? joules and only joules because it's a change in potential energy. And you could have adopted this equation to get delta U and add the Q inside it. You could have turned around and said, oh, I'm not going to do that. I'm going to say delta U is equal to KE big Q little q times 1 over RF minus 1 over RI. And that would have worked just as well. You know, I chose to deal in terms of voltage, and then I brought my Q in to convert it into an energy. So, okay, yes?
So the delta V formula by itself always uses big Q?
The delta V formula is the potential. The height is caused by the mountain, not your backpack. Though there is a height to your backpack. Yeah, so it's like you got to pick out which is, and that's why I got to be a bit careful writing the questions. I got to have a clearly big charge and a clearly little charge. Although clearly it works even if the charge is about the same size. Yeah.
Why did you multiply it by 2?
Because to go from my change in potential, which is about just, I got to multiply by the charge of this little charge. Yeah. Cool. If you remember in physics 1, there was this thing where you did mgh is equal to PE, and then I don't know if you learn it that way. I hope your teacher turned around and said, "Well, that's your change in potential energy. That's delta PE. Some do, some don't." But whether they did or they didn't, then inevitably came the question of, well, what is my potential energy? And so we went through this long discussion about, well, I should really measure from the bottom of the room? No. The bottom of the planet? No. The bottom of the sun? No. The bottom of the galaxy? No. The bottom of the local group? No. The bottom of the, where's the bottom of the universe? Where is the lowest gravitational point in the universe? And we have no idea. So we don't know how low it is. But I know if I go infinitely far away, infinitely, what does that mean? Just a long, 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 long way away from any other mass, I'm effectively as high as I can get. I don't mean that I'm effectively as just like, it's like I can move and there's no force acting on me, so it doesn't matter. Once there's no force acting on you, motion is basically free because there's no force acting on you. So all I've got to do is get a long way away from anything. So I get a long, long way away from anything. And so what I recognize is, so that means I can find the potential at that table by taking the other point as not the floor, but the other point has been infinitely far away. So what happens is I go, well, okay, it's the same equation, KEQ 1 over RB minus 1 over RA, but 1 over RA, my starting point, was infinitely far away. So that's 1 over infinity, and that goes away. So I end up with this really simple expression, KEQ over RB. I don't learn that. I know that one. Clearly, I know that one with a negative sign in it, but ignoring that. I know that one. And if I want to find the potential, I just get rid of that. So what sounds like it's going to be a really complex problem just becomes mathematically trivial. Notice, as I go farther and farther away from a mass or a charge, whatever, my force versus distance, not inside the charge but outside the charge, is what? Inverse or inverse square?
Inverse.
What's the equation? So what's the inverse square? Yeah. And my electric field, what's that going to be? Inverse or inverse square? E is equal to KEQ over R squared, inverse square. My potential is 1 over R, which is inverse. So this is inv square. This is voltage is equal to KEQ over R. And my electric field is, not my electric field, my U is KE big Q, little q over R. So isn't that kind of like, I don't know what you feel about that, but I feel like, oh man, that's kind of giving me the pattern, isn't it? Force is inverse square, and it's Q1 and Q2. Electric field is inverse square, but it's just Q, because it doesn't depend upon the little charge. And potential energy is inverse, but it's Q1 and Q2. And voltage is inverse, but it's only Q. So if you kind of like double down and learn that one really well, and learn that one really well, you can figure out the other two very easily. So they're not four independent equations. They're all related to each other. They're all different aspects of the same thing in the end. What is electric potential at a point that is 3 meters from a 2 coulomb positive charge, 3 meters away? P. My potential is equal to Ke Q over R. My potential is equal to Ke. What's my Ke? Oh, Ke. No. What's my Q? My Q is +2 over my R. R is 3, which equals 0.66 Ke volts. Mathematically a piece of cake. So I think that, I don't know how you are, but I think that stuff like that, putting those things side by side on an equation, on a paper. Notice, we're not talking about the change-in and the change-in. They're a bit more complicated equations. We're talking about the gravitational potential energy and the gravitational potential associated with a certain position. But you see a symmetry in that. Okay. Suppose that we have a whole bunch of charges. I have a point of interest. Let's say there's a whole bunch of charges. What do? I just add them all up. I do the potential caused by this guy is that, and the potential caused by that guy is that. These are, is potential, is it a vector or is it a scalar? So then I don't have to worry about the direction, do I? All I have to worry about is its magnitude. So you work out that magnitude and add it to that magnitude and add it to that magnitude. It's a piece of cake. Electric potential energy due to pairs of charges. So now I have pairs of charges. We know my potential energy is Q times my voltage. I know my voltage is KEQ1. I prefer little q's and big q's. I don't know why, but I do. So then I end up with this thing where it goes, oh, it's the little q times that, which is KE little q, big Q over the distance between them, between them. Well, that fell out. So if I have a whole bunch of them, what do? I just add them all up. So it's the first pair multiply over its separation, added to the second pair of charges multiplied, divided by that separation, added to that pair, divided by that separation. We know this. We did this before. Electric field equals my change in potential over my change in position. So that's already taken care of. We don't need to derive that. Potential. Let's say we have so many charges, they're not in pairs. Let's say we have so many of them. What do? I'm sorry, no. I have a ton of charges. It's not like that. I have a cloud of charge. What do? Well, I don't sum, I integrate. I integrate, I get that. Everybody sits up. Don't care about that one. Don't care about that one. All I care about is this one. And I don't even care about it in terms of integration, because let's think about it. It wants to know the potential on the axis which goes through a ring of charge. Okay? So, I say, well, my potential is equal to KE times the mother charge over the separation. What's the mother charge in this case? It's all the little dq's added together. Oh, it's the integral, if you like. Okay, so what's the, and that's dq. Well, if I integrate all my dq's, I get q, so this is keq. And the r's are all the same, aren't they? The distance from that little dq to my point of interest is the same as the distance from that little dq to the point of interest is the same as the distance from that little dq to the point of interest. And it's Pythagoras. It's going to be the square root of x squared plus a squared. So it looks like a piece of work. It looks like, oh my word, you've got to be Albert Einstein, or if not Albert Einstein, Robert Hooke to work that out. Although Robert Hooke was probably just as good at math. But turns out it's pretty straightforward when you visualize it. Okay, so I used to ask this question, and then I'd find, well, the answer's like, you know, once you figure it, people would go, oh, that's an obvious answer. We're doing this integration for no real reason because the symmetries are so great. So I don't actually ask so much about that now. You know, just know how to get the equation. It's like, oh, it's just the total charge divided by the Pythagorean distance. You know, that, not that, and not that, but that, which is what it always would be. Last little bit, electric potential. Inside the electric potential, inside, it's a constant potential. Outside, it folds up as an inverse relationship. Electric field, inside, it is zero. We did that with Gauss's law. Outside, it's an inverse square.